My name is Min Kai, and I'm from the Academia Sinica Institute of Astronomy and Astrophysics in Taipei, Taiwan, and I'm going to be talking about dust in protoplanetary disks. Now, before I begin, I want to quickly introduce where I'm coming from. So, the Academia Sinica is the sort of research branch of the government of Taiwan. So, we are a pure research institute, so we don't have professors per se, but we have research fellows. And one of the nice things about being part of the institute is that our research fund is actually part of the federal budget, and we can get additional grants from our Ministry of Science and Technology, and we have quite a few country-specific grants as well, including the UK. So the Academia Sinica Institute of Astronomy and Astrophysics is one of the newer institutes in the academy. So we are physically located in National Taiwan University. So it's kind of like how CETA is located in University of Toronto. We also have an office in Hawaii. We have about 40 faculty, about 50 postdocs, about 30 engineers and 30 students. And the total number of people from top to bottom is about 200. And so I am affiliated with the theoretical division of the Institute, the Theoretical Institute for Advanced Research in Astrophysics, or TIERA, but we are also involved in a bunch of other projects, actually, including ALMA. Actually, one of our biggest projects is ALMA. And even though we are in Taiwan, we actually have an English working environment because we have quite a large fraction of international staff at the Institute. Now, as I said, I am a theorist, but even I can appreciate a good view from the office. So, with that plug out of the way, let's get into the science. So, I am interested in planet formation. Okay, and this is a plot of all the known exoplanets so far, discovered so far. Plotting here mass against separation from its central star, and there's almost about 4,000 exoplanets discovered so far in almost 3,000 planetary systems. And these exoplanets actually come in a wide range of orbital configurations, right? They come in all shapes and sizes. So we've got planets that are closely packed. So this is a multi-planet, closely packed multi-planet system. We've got very massive planets that are very far away from their central stars. So this is probably the most famous example of the directly imaged planets around HR 8799. And these planets are tens of AU away from their central stars, so quite far out. We also have planets that are in quite complicated orbital configurations. So in this case, this exoplanet here is orbiting its central star, but this star-planet system is being orbited by a binary. So this planet actually has three stars. So what we would like to understand is how do these systems come to be, right? And the basic picture of planet formation is the following. So it's generally thought that we start off with a molecular cloud that is overdense and collapses under its own gravity. And in the center of this cloud, you form a protostar. And around the protostar, you form a protostellar disk. And then through some kind of magic, planets are born in these disks. And when the disk goes away, we are left with a planetary system. Now we can actually observe. Well, we observe the final product of the sequence quite regularly now, right? There's almost a new planetary system being discovered every week. But in order to understand why the final system looks the way it is, we sort of need to look backwards in time a bit and look at the planet formation stage. And fortunately, we can do that actually because of instruments like ALMA. So this is a ALMA image of the disk around H.L. tau. Now you notice this is not the H.L. tau image, but this is a observation done by one of our previous postdocs, Yan Shiwei, and he's showing the essentially the dust distribution and also the gas distribution. And what we see here is that the disk actually contains narrow gaps. And here's another example of a protoplanetary disk with a ring or a gap in it. And one of the ideas is that, well, maybe these gaps are actually carved by planets in the disk, unseen planets in the disk. So they could be actually footprints of ongoing planet formation. And in addition to rings and gaps, we actually also see spiral arms in disks, and sometimes we see lopsided disks. So these are disks where the dust distribution is only concentrated on one side of the disk. Now, I think it's agreed that in order to understand planet formation evolution, you simultaneously need to understand disk dynamics, because what goes on in the disk affects planet formation, but once you have planets forming and evolving, those also affect the disk as well. And there are quite a few basic questions we are still asking in this field. So for example, how do protoplanetary disks actually accrete onto the stars? Are these disks turbulent? If they are turbulent, what are the sources of turbulence? Um, what are the origins of rings and gaps and spirals? Are they to do with unseen planets, or is something else happening? So obviously I don't have time to touch on all these topics, so I'm just going to talk about one subtopic, which is dust-gas interaction. And this is clearly an important topic because that's what we think makes planets, right? So the basic idea of planet formation is that you start off with small dust grains and they stick together and then somehow form planetesimals. And then these planetesimals coalesce together to form protoplanets. Now, uh, the in a protoplanetary disk, it's about 99% gas and only 1% dust by mass. But we care about that 1% because that's what makes planets, right? At least in this sort of core accretion scenario. Um, so we need to understand how dust and gas interacts, right? To understand how dust actually evolves into um, protoplanets. Now, this is not only important for theoretical planet formation, but also for explaining observations, because very often what we see in gas and what we see in dust are different. In fact, more often than not, when we look at observations, the observations tell us about the dust distribution. And this is also another local result obtained by Tang Yawen at the Institute. So, and here are the couple of examples of what dust-gas interaction might involve. So dust particles can collide with one another, and when they collide, they can fragment or they can stick together to form bigger particles. Dust particles tend to drift actually to the star, and I'll talk about that a little bit later. Dust particles can sink to the midplane of the disk due to the vertical gravity of the star, but if there's turbulence in the disk, they might get stirred as well. And on the right shows that depending on what wavelength you observe in, you might be looking at different layers in the disk because different particle sizes may be distributed differently vertically. So um, now modeling the interaction between gas and dust is an incredibly complicated business, and really there is only one proper way to do this, and that is to actually simulate a continuum of fluid, the gas, interacting with n particles. And for each particle, you track its evolution through the gas, and every time step you calculate the dust-gas interaction between each particle. Now, this represents the state-of-the-art approach, and if you want to do anything realistic, this is really your only option. So I'm not here to take anything away from this approach. It's the right way to do things. But I think it's also fair to say that this approach, even though it's state-of-the-art, it's also computationally very expensive. You need very big computers, and you need to develop very clever algorithms to capture this interaction properly. And sometimes these simulations are also very complicated, that it's not straightforward to extract what is physically going on in this. So I wanted to ask if there's a simpler way to describe dust and gas dynamics. So I'm going to try to build a simpler description of dust-gas dynamics in a protoplanetary disk. And the first question we can ask is, well, what kind of features do we want in this model? And one of the basic results we know in a protoplanetary disk is that dust particles tend to drift. And you can understand this by considering the following. So suppose we have a pressure profile in the disk caused by the gas. Now, the dust particles, though, the dust particles will always rotate around the star at the local Keplerian speed. But the gas will rotate at a different speed than Keplerian, depending on the local pressure gradient. In a typical situation where pressure decreases outwards, the gas would be subcaplarian. That means if you are a dust particles, you would feel a headwind, and that would actually rob you of angular momentum because of the friction with the gas. And if you're losing angular momentum, you would be drifting inwards towards higher pressure. And you have an opposite argument if you had pressure increasing outwards. So the basic idea is that the friction between gas and dust tends to cause dust particles to drift towards high pressure. That is a physical fact. But I want to describe a thermodynamic view of the consequence of this particle drift. Now, to first approximation, we can kind of think of the dust particles as a pressureless fluid, right? So they are just solid particles orbiting around the star at the Keplerian speed. So they have no internal pressure per se. So since they have no pressure, we can kind of think of the particles as the cold phase of this dust-gas mixture. Now, from this point of view, when I have dust particles drifting from low pressure to high pressure, therefore a particle flux, and because particles are the cold phase of the medium, I can think of a particle flux as a negative heat flux. So that's the basic idea. Now, based on this idea, we actually found a connection between a system that is composed of dust and polytropic gas interacting via drag and standard textbook hydrodynamics. And this connection or this approximation works better and better the smaller particles you consider. And this is the set of equations that describe dusty gas in our model. Now, those of you who are familiar with hydrodynamics will recognize these three equations as just the mass conservation, momentum conservation, and the energy equation for standard hydrodynamics. I have a slightly weird source term in the energy equation, but on the surface, these equations look like gas dynamics, even though they are physically describing dusty gas, two-phase medium. And as I said, there's a slightly unusual source term in the energy equation that models particle drift. Now, because this set of equations are so similar to hydrodynamics, that means we can adapt existing hydrodynamic codes to simulate dusty gas without too much effort. So we've done this for the Pluto code. I put implementation in quotation marks because I did not actually implement anything because Pluto already solves essentially the set of equations. So all we had to do was to change a few symbols in one of their modules, actually. And the neat thing is that the code itself does not know it's simulating dusty gas. Right? So it still thinks it's doing hydrodynamics, even though we can get dust information out of the simulation. So I now just want to show you a couple of applications of this this model. I'm going to show you some. You can actually get some of the basic results in dust gas dynamics just from these three equations. So as I said, particle drift is inbuilt into this model. And here's an example of that. So here I'm considering a two-dimensional flat disk, and I've put in a 10 Earth mass planet in the disk. And the planet opens up a gap, a shallow gap in the gas, but that shallow gap involves local pressure fluctuations, and dust particles respond to that, and they tend to accumulate at the gap edges. And as you can also see, the gap in the dust is much deeper than the gap in the gas. Now, if I increase the planet mass to 30 Earth masses, then I find also a deep gap in the gas. And in fact, the gap edge is actually unstable to what we call a vortex formation, which is essentially the formation of a local radial and azimuthal pressure bump. And these vortices are actually known to be very efficient at trapping dust particles. And as you can see in the dust distribution, there's a very high overdensity in dust, more than order of magnitude compared to the almost order of magnitude larger than the gas overdensity. So these simulations. Oh yeah, I forgot to mention. So The vortex scenario is also one of the ideas to explain observations like these, right? So this is an actual observation of a azimuthal or radial dust trap around a star, or in a protoplanetary disk. So one of the ideas is that, well, maybe this can be explained by an unseen planet opening up a gap and forming a vortex, which then traps dust particles. Now, in these simulations I've done so far, I've assumed a low dust-gas ratio, but there's another test we can do in the limit of high dust-gas ratio, which is the streaming instability. So coming back to this picture of planet formation, which of planet formation, so the basic idea is that dust grains first need to coalesce to form planetesimals. And so the question is, well, how do I get from small dust grains, like micron or millimeter sized dust grains, to planetesimals, right, which are much, much larger, like kilometers or 1,000-kilometer objects, right? So there's something called the streaming instability, which is a instability that is caused by the interaction between gas and dust. So it relies on the dust being affected by gas and the gas being affected by dust. And this is a numerical simulation carried out by Anders Johansson. As you can see, if you start off with some small fluctuations, then these fluctuations grow very quickly and you form very dense dust clumps. So the nice thing about the streaming instability is that it is an analytic problem in a linear regime. So you can use it to test your code. So this is the streaming instability using the my sort of modified Pluto code, single fluid code. And as you can see, I get a pretty good match between the linear growth of instability in the simulations. And if I look at the saturated state, I also find expected results. So for large-ish particles, I get very dense. I can get high overdensities in the dust. But for smaller particles, I only get order unity fluctuations for the timescales I've simulated. And here's a more recent calculation of a stratified disk, actually, of the streaming instability. Now you will notice that there's actually a lack of particles on the right compared to the left, and that's because this is actually a global simulation. So the entire dust clump is actually migrating inwards. So the streaming instability is a pretty promising way of forming planetesimals, actually. But there's one catch, and that is you sort of need to start with the local dust density being higher than the gas density in order for this instability to be efficient. There is instability at all dust-to-gas ratios, but in order for this to be of any importance, you usually need the dust-to-gas ratio to be larger than 1. Now, we know that the dust-to-gas ratio in the ISM is about 1%, so how do we actually get this, how do we meet this condition? Now, the traditional idea is that, yes, you do start off with a young disk where the dust particles are very well mixed with the gas, so the local dust-to-gas ratio is about 1%. But over time, the dust particles settle to the midplane, and the idea is that they settle to a very dense midplane layer where the dust-gas ratio is approaching 1. And at that point, you can then have streaming instability making planetesimals. And indeed, this is an actual simulation, again, using the modified Pluto code. So again, I'm distributing my dust particles. I have a uniform dust-gas ratio initially, and then after some time, the dust particles sink to the midplane. But I've actually carefully tuned my disk parameters to avoid any turbulence developing in the disk. Okay, so if the gas is laminar, it's not doing anything crazy or chaotic, then dust particles can simply settle to the midplane. So the question is then, are protoplanetary disks actually laminar, right? Do they just sit there quietly, letting the dust particles sink? Well, actually, there's been a lot of discussion on possible sources of turbulence in protoplanetary disks. For example, magnetorotation instability to do with magnetic fields, gravitational instability to do with self-gravity of the disk, elliptic instability to do with the topology of the flow, and a bunch of others. One thing I'm going to focus on is something called the vertical shear instability. And this is a hydrodynamic instability that is that could be actually pretty common. So the idea is that if you were to, so we're talking about Keplerian disks to a very good approximation. Right? So the rotation of the fluid around the star, of the disk around the star, is described by the Keplerian speed. But actually, if you were to work out the disk structure in detail and exactly, you will find that it's actually a Keplerian rotation plus a small correction, and this correction actually depends on height away from the midplane. So in other words, there's vertical shear, right? So the midplane of the disk actually rotates slightly differently than the atmosphere of the disk. And whenever there is shear, there is free energy. And if there's free energy, it means there could be an instability that can tap into this free energy. And indeed, if you put this into a simulation, this is a typical result you will find. That the disk actually develops an instability, which involves very large-scale vertical motion. So I'm plotting here the vertical velocity in the disk. So the disk actually undergoes these large-scale vertical sloshing motions. And so you can imagine this might be bad news for planet formation, because if you want the dust particles to settle to the midplane, but the disk is actually undergoing large-scale vertical motions, it's not clear if the dust particles can actually settle. So using this modified Pluto code, I've looked into this problem. So here I'm comparing two simulations. On the left there, I've assumed a dust-gas ratio of 1%, so solar metallicity. And in this case, the dust particles remain actually well mixed with the gas. So there's no sign of settling there. But if I increase the dust-gas ratio to 3%, so supersolar metallicity, then I can get some dust settling, especially in the inner disk. I want to point out that these are relatively high-resolution simulations, about 240 cells per scale height, and it also includes the back reaction of dust on gas. So the dust is not just a passive. It's not just passive. It actually also affects the gas motions. So so this is just the supersolar metallicity simulation further into the simulation. And I'm plotting here the dust-gas ratio and also the vertical velocity on the bottom. And as you can see, actually in the inner disk, it's actually relatively quiet where dust has built up, and that's actually because we included the back reaction of dust on gas. So the point of these test simulations is to show that dust settling is not a universal phenomenon, right? It does depend on parameters. But if you are in those parameter regimes where you either have supersolar metallicity or if the disk doesn't develop turbulence, then in principle you could get very dense midplane particle layers, and that hopefully would lead to planet formation. So this following question is that, well, then you could imagine a situation where a planet is born into a dust-rich environment, right? If being dust-rich is a requirement to form the planet in the first place. So then that got me thinking, well, is there something interesting happening when we consider disk-planet interaction in the limit of high dust content? So this is so I proposed this as a summer project last year. And this project done with an undergraduate student at NTU. So we're just looking at the problem of disk-planet interaction, which has been well studied. But we are going to look at this problem in the high dust-to-gas ratio limit. Now, typically what happens when you put a planet in a disk is that it launches spiral density waves. And these density waves actually exert a torque on the planet. And also the material near the planet's orbital radius also exerts a torque on the planet. And the planet would respond to these torques by migrating. So we wanted to we wanted to know what happens to planet migration, or disk planet torques in this scenario, and in the limit of high dust gas ratio. Now here are the results. Wait for the yeah. So on the top there, I'm considering two simulations. One where the stopping time is zero, so literally zero-size particles, and perfectly coupled with the gas, and one simulation on the bottom with slightly decoupled um, particles with the gas. And the left plot is the torque acting on the planet, and as you can see, the torque on the planet in the case of zero stopping time with zero particle sizes oscillates for a bit, but it settles to a constant value. But in the case where the dust particles are slightly decoupled, the torque oscillations actually remain relatively large amplitude for a long time before it starts to show any signs of converging. Now this is actually a movie, and what I'm going to show is both the surface density of the disk around the planet, and also a quantity called the potential vorticity, which is the vorticity divided by the surface density of the disk. Now the PV is essentially a tracer for the fluid, so you can trace individual fluid elements by plotting the PV. So if I play this video, you'll see that in the stopping time equals zero case, we don't get a lot of features in the surface density, but in the slightly decoupled case, we actually create this sort of bubble in the surface density around the planet. And also in the potential vorticity, mixing happens in these zero particle size case, but in the case where the particles are slightly decoupled, I actually form a blob in the potential vorticity. So this is just comparing a few snapshots of that movie where the stopping time is 0 and the stopping time is 10 to the minus 3. So perfectly coupled and slightly decoupled. So this plots the surface density, and as you can see, we actually, in the case where the dust particles are slightly decoupled, we create this bubble inside the planet's orbital region, and that naturally leads to very large torque oscillation. So this comparison is the torque per unit length around the planet for the perfectly coupled case on the left and the slightly decoupled case on the right. And as you can see, over time, the zero stopping time case just damps to 0, but the slightly decoupled case, the 110 to the minus 3 on the right, the torque actually remains oscillatory. There's a spike at the planet's location. Now, because of this connection between this dusty gas model and original standard hydrodynamics, we know from standard hydrodynamic simulations of disk planet interaction, that's the pure gas limit, that torques coming in from the orbital region of the planet is actually related to the potential vorticity in that region. So indeed, when we plot the evolution of potential vorticity in these two simulations, we see a qualitative difference. If the stopping time is 0, the PV mixes up in the orbital region. We have a flat distribution, and that implies that actually means 0 orbital torques. But in the case where in the case where the dust particles are slightly decoupled, we actually generate potential vorticity in the orbital region. So we have a PV blob here. Then the question is, well, how do finite particle sizes generate potential vorticity, right? And it really boils down to the fact that when you consider dusty gas, it is actually a baroclinic fluid because the pressure only comes from the gas, but the total density comes from gas and dust. So there is actually no reason why the dust and gas are aligned. Contours of constant dust density and constant gas density are generally misaligned, and that actually implies a change in the potential vorticity. And here's a plot of the misalignment between gas and dust in the case of stopping time 10 to the minus 3, so slightly decoupled, and you can see it is non-zero near the planet. That means when fluid particles pass by the planet, they can actually pick up potential vorticity. And here's another simulation where similar simulation, but he's started with a dust gas ratio of about 1. And in this particular simulation, the orbital region actually becomes unstable to vortex formation. So in summary, so what we found in this summer project is that when you have a finite particle size in the limit of high dust to gas ratio, you can actually sustain these large amplitude torque oscillations acting on the planet. Now, there are a couple of interesting implications. That is, the torques we measure are still negative, so the planets would still migrate inwards. But what we know from disk model is that we tend to find larger particles and higher metallicities in the inner disk. So a planet might start off in the outer disk, but as it migrates inwards towards a region of larger particles and higher dust-to-gas ratio, the torques acting on the planet might start to become more oscillatory. Or if there's grain growth around the planet, right, that might also enable oscillatory torques. So this is just an experiment I did for fun, where I assumed a stopping time or 0 particle size up to 1,000 orbits. I stopped the simulation and restarted, but I just assume the stopping time is now 0.01 or finite particle size, and we see it immediately. It starts to develop torque oscillations. So this could have interesting implications for the eccentricity evolution of the planet, and also as I mentioned. And under some conditions, the disk is actually unstable to vortex formation in the planet's orbital region, so that could have further complicate this entire picture. So, in summary, what we've done is really just to build a bridge between dusty gas dynamics as a physical system of interest and standard hydrodynamics plus cooling. And this framework or this model is by no means a replacement for actual dust particle gas interaction simulations. But what we're hoping this model can provide is that it might be useful in getting an understanding of what is happening in dusty gas in the language of hydrodynamics. And also, because there are already many interesting results in the pure hydrodynamic case, by building this bridge, it might lead to discovery of equivalent or analogs of known hydrodynamic results as well. So that is that's almost the end of my talk. Final plug, we have a summer student program this year, again, for advanced undergraduate students or beginning masters. So if you're interested, you can have a look at the website. And also, we are holding a summer school on origin of solar systems in Taipei in SIAA. So if you're interested in these events, you can talk to me, or you can look at the websites. And thank you very much.